Good day mga ka-CRT, welcome again to our channel. In this video lecture, I'm going to discuss electronics lecture series. This is season 2, all about BJT DC analysis. For this episode, episode 6, we will discuss specifically the voltage divider bias. I'm Engineer Joshua B. Ancheta, your lecturer. I already uploaded the Season 1 of this electronics lecture series. Season 1 is about semiconductor and diode. Season 1 is uploaded in the year 2022. So that was 2 years ago. And these are the following episodes. So episode 1 is about introduction, episode 2, semiconductor theory, episode 3, the diode, episode 4, diode in DC circuit, Episode 5, half-wave rectifier. Episode 6, full-wave rectifier. Episode 7, clippers. Episode 8, clamper. Episode 9, voltage multiplier. Episode 10, Zener diode. And Episode 11, special purpose diode. So you can visit this video lecture in our YouTube channel. Just look for the playlist Electronics Lecture Series Season 1. This is the circuit of a voltage divider biasing network. So again, we will be using common emitter configuration with NPN type transistor. As you can see, we still have RC and RE resistors. And for the base terminal, there are two resistors connected in a voltage divider network. We have R1 and R2. And as you can observe, in voltage divider bias, there are four resistors in the circuit. Let us now derive some equations. First, we have to get the Thevenin's voltage. This is equivalent to VCC times the lower resistance R2 over R1 plus R2. And we have Thevenin's resistance of R1 times R2 over R1 plus R2. This is the parallel connection for R1 and R2. And then, we have to check for or test for approximation. So for the test for approximation, we have to check this condition. Beta RE greater than or equal to 10 times R2. Okay, so let us bring the condition here. If this condition is satisfied, the circuit can be converted in this way. So this is the transistor. You still have the VCC and the resistor RC. You still have RE and ground. And for the base terminal, this is just equivalent to the Thevenin's voltage. If the condition is not satisfied, the equivalent circuit is this. The transistor, the VCC and the RC, the RE and the ground, the RTH and the VTH. So, these are the two conditions for the test for approximation. Then, after that, we can now get the base emitter loop. So for the base emitter loop of the first figure, this is VTH minus VBE minus IE RE equals 0. And we can approximate IC approximately equal to IE. For the second figure, the equation is VTH minus IB times RTH minus VBE minus IE RE equals 0. Let us now solve this example. But first, we have to test for the approximation. So, test for approximation is beta RE greater than or equal to 10 R2. Beta is 100. RE is 1.5 kilo ohms greater than or equal to 10 times R2, which is 3.9 kilo ohms. As you can observe here, we have 150 kilo ohms greater than or equal to 39 kilo ohms. And the condition is satisfied. So therefore, we will use the equivalent circuit. So the equivalent circuit is, this is the transistor and the VCC RC. So this is 22 volts. This is 10 kilo ohms. Then the RE 1.5 kilo ohms. And during DC analysis, you can omit the capacitors. So you can remove that in your DC analysis. Then for the base terminal, this is the VTH. So let us now solve the required parameters. We will start with the calculation of VTH. This is 22 volts times R2, 3.9 kilo ohms, all over R1, 39, plus R2, 3.9 kilo ohms. So solve that using your calculator. And this is equivalent to 2 volts. Okay? So VTH is 2 volts. Although not required, let us also solve RTH. So this is R1 times R2 over R1 plus R2. So the equivalent of that is .54 kilo ohms. So 5454 is repeating. For the BE loop, let us now solve or derive or write the equation. So from the BE loop, VTH minus VBE 0.7 minus IE RE equals 0. VTH is 2 volts minus 0.7 minus IE, we are solving IE here, times RE 1.5 kilo ohms. And IE is approximately equivalent to IC. So let us solve IE and IC. 2 minus 0.7 over 1.5 kilo ohms. And using 4 decimal places, we have 0.8667. So this is in milliampere. So this is our answer in the current requirement. Next, for the CE loop, so this is the CE loop. Therefore, we have 22 minus of the current IC, ICRC minus BCE minus IE RE equals 0. So 22 minus ICRC, let us direct that to our calculator. 0.8667 milliampere times RC, which is 10 kilo ohms. And this is, the product ICRC is 8.667 volts. Minus BCE, this is the unknown. Minus IERE, so direct that in our calculator. 0.8667 milli times 1.5 kilo ohms. And this is 1.3 4 decimal places 001 equals 0. Then from this solution, we can now solve BCE. So 22 minus 0.8 or 22 minus 8.667 minus 1.3001. And BCE is 12.0329 volts. This is the end of this video lecture. And also, this is the end of Season 2 Electronics Lecture Series. See you in Season 3 of my Electronics Lecture Series. Thank you for watching. You can leave a comment and please share, like, and subscribe to this channel. Thank you and God bless you all.